Hi everyone, this next video is going to show us how to find the roots of complex numbers, and here's a good question that I've got for us. So z cubed. Now it's best if we consider these complex numbers in polar form. So I'll write r says theta cubed equals, and now we need to figure out this in polar form. So I could draw an argument diagram, and this complex number would be one step on the real axis and then downwards by root 3 steps, leaving us with an argument and some modulus there. Now hopefully we recognise this as one of our special triangles with the hypotenuse length there would be 2. You could use Pythagoras for that, and the inverse tan of this ratio would give us an argument of negative pi over 3. Now if you weren't quite up to speed on that, you could use your graphing calculator on a tech active exam. So we need to go to options, then to complex here, F3, then F6 to get to the next menu, and these are the ones we're interested in. So I will input my complex number 1 minus I, sorry, I got 11 then, minus I by the square root of 3, and then I'll press this F3 key, which will convert to polar form, r and theta. And there it is, it's 2. This is the symbol the calculator uses for cis, 2 cis negative pi over 3, which is just a confirmation of what we had there. That's nice. So using de Moivre's theorem, this doesn't want to work for some reason. Let's make sure I'm still here in OneNote. I've got r cubed cis 3 theta equals 2 cis negative pi over 3. So we will now consider r cubed equals 2. R would be the cube root of 2. That's the easy part. We will also consider the fact that 3 theta equals negative pi over 3. But don't forget, this is not the only solution. We could also have any number of full rotations, so 2 times k times pi. Now because we're dealing with a cube root, I would expect 3 unique solutions. So I will say that k can have the value 0, 1 or 2 to give me 3 unique solutions. So no rotations, a full rotation or 2 full rotations compared to this starting point. Now how will this play out? Well, first we have to let k equals 0. We would have 3 theta equals negative pi on 3, so theta is negative pi on 9. That's our first argument. If k equaled 1, 3 theta would be negative pi on 3 plus 2 pi. So that is negative pi plus, let's have it all over 3 to start with, that would be 6 pi. That's still 3 theta. I think we can figure this out. That 6 minus 1 would be 5 pi. Now if I divide by the 3, it'll be 5 pi over 9. So that's good. It's still within the range for the principal argument between, I'll just make a quick note that we always want to express our arguments between negative pi and positive pi. We call that the principal argument if it's within that limits there. And now we have k equals 2 to give us the third possible answer. 3 theta would be negative pi over 3 plus, and if we jump back to there for a minute, 2 times 2 is 4 pi, so we'll be adding 4 pi. Let's add this, so making a common denominator of 3, 3 fours are 12 pi, 12 take a pi would be 11 pi, and if I divide through by that 3, it's 11 pi over 9. Now 11 pi over 9 is greater than pi. So a quick few thoughts about this. 11 pi over 9 is here. I would like to know how much that is the same as. That is equivalent to negative 7 pi over 9 as a principal argument. Just write that again, that's a little bit too messy. Negative 7 pi over 9. So I haven't actually, I've calculated all the bits that I need, but now I'll write the solutions. So Z0, if I run back to here, I'll see that the modulus is cube root 2, and in the first case our argument was negative pi over 9. So cube root of 2 is negative pi over 9. Now, sometimes they want these expressed in rectangular form, so we could do this. We could literally go the cube root of 2 by cosine of negative pi over 9 plus the cube root of 2 by the sine of negative pi over 9 times I, or we can just use the built-in conversions here. So let's do it that way. We'll go cube root of 2, and the cis symbol is just there. Our argument is negative pi over 9, so let's put that in brackets to make, oh, it probably wouldn't need to be, so negative pi over 9, that's good. And now I want this to be in Cartesian form, and I didn't expect it to be nice numbers with something like cube root of 2, so let's write this to, what have we got, 1.18 and negative 0.43. I'll round off to 2 decimals, 1.18 minus 0.43 I. Our next one was 5 pi over 9. And our last one was negative 7 pi over 9. And once again, if you do these conversions, I did them before I started, so I won't show the calculator. I had negative 0.22 plus 1.24i for that one, and I had negative 0.97 plus, sorry, that's a minus 0.81i. And if you had to show them on an Argand diagram, we would draw ourselves a real and an imaginary axis. Now it's much easier to think in terms of the polar coordinates, not the rectangular coordinates. So our first one, they're all the same length, and our first one is at negative pi over 9. So let's give ourselves, there's Z0 at a small angle there of negative pi over 9. Now, because there are 3 of them, they'll be equally spaced around the complex plane. The next one is at 5 pi over 9, so that's just a little bit past pi over 2. And then the next one is negative 7 pi over 9, so it'll be down here. This is Z1, this is 2. Of course, they all have the same length, so I would be able to have a circle going around there, and the radius of the circle, the length of the modulus, would be cube root 2. And that's my very, very rough Argand diagram for these. That's how you do the roots of a complex number. It turned out in this case that our complex number, all of the roots were complex. None of these were on the real axis. And there's no real need for that. So it's a cube root, so 3 unique solutions. Okay, that's it for now. See you next time.